Hello, everybody. Can you hear me?
I hear you perfectly.
Hi, Dr. Garret. Welcome. We were waiting for you.
Good
Thank
morning.
you.
Good morning.
I'm looking forward to it. I think everything's all ready, I hope.
Well, don't worry about it. Just
Okay,
carry on between friends, right?
exactly. What I'd like to do is all the participants today, I'd like to send a copy of my latest book that I can do because I self-published it. It's this book right here. Some of you all might already have it, but I will give a,
Oh,
I will, well,
yes,
of course, the
yeah,
electronic.
that would be great.
Yeah, can I purchase the book? If you send me the info, I'll buy it. Or if you send it to me, I'll say thank you.
Well, I'll send you right away the electronic version that made the book.
Oh, okay.
So, and then, well, sure, you can always get a hard copy. It's on Amazon.com.
How
Okay.
did you publish it, Garret?
I used Amazon, KDP it's called.
Ah,
It's
I see.
great.
So
You
it's an
know,
Amazon self-publishing service.
Exactly, it's great, so it gives you the freedom. I'm only charging $12.25. You set the price and, everything else for the book.
Could you tell me, please, could you tell me the title? Because I couldn't read it with my eyes.
Okay, it's called Matrix Gateway to Geometric Algebra, Space-Time and Spinners. It was
Oh, yes.
published in 2019, November 2019. I think,
Yes, I am interested. Yes, indeed. Thank you.
I think Professor Cruz has a copy of it. I gave a copy to people at FESC.
Okay.
And I'm certainly willing to give a copy to anyone that attends the lecture today. I'll give some other references as well, but unfortunately, I won't be able to give a copy of this book with Hestenes. This was published by Rydell.
Oh, yes.
In 1985, and then later republished in 1992. But I cannot give a copy of that because that's copyright and all the rest of that. It's unfortunate that these publishers now jack the price up to over $100 or whatever it is. It's so.
Yes, it makes it somewhat inaccessible unless you especially if you're no longer associated directly with an institution of some sort.
Yeah, exactly. So
Even then, the actual purchase of books or technical books is down to, minuscule numbers, very, very, very few sales, books, unfortunately, especially with the advent of the electronic version. And yeah.
Anyway, so basically my talk today will be about a chapter from this book here on space-time algebra. But when we get started, I'll share screen and we can get started. I don't know.
Okay, maybe we can wait a couple of more minutes in case
Okay.
another participant shows up. In the meantime, I will use go through my usual little startup, and I'll share this screen that contains the agenda.
Now, by the way, so if people send me their email address, I can send them a copy directly, even during or after my talk, whatever. But of course, I guess all the email addresses are on your seminar page, but it's just a matter of the ones that attend. I will only give the book, of course, to people that attend
Yes.
the lecture.
You have my email, Dr. Garret? You have my email, Ruggero Santilli?
I believe
you.
it's on all the.
I sent you a couple of emails. You should have it in your.
Oh, yes, I have it. So I'll send you a copy directly.
Great, thank you.
Yes, and me too, please, Garret.
Oh, okay. Yeah, I thought maybe I had already sent you a copy, but maybe not.
I think you. I can double check. I believe I may have received a copy from you maybe as much as 6 months ago. Is that something like that?
Anyway, so I'm willing to share with other people too if they want it. It's no big deal. I believe that science should be distributed. It's kind of the same philosophy as with his journal that he has. Science should be open, not closed.
Yes, absolutely. Yes, indeed.
So hadronics was pretty well open as well, which is very nice.
Yes, it's unfortunate that scientific publishing has sort of reached this stage, you know, where
Well, that's the nice thing about this HD. Well, there are many actually. There's many other publishers that allow you to write your own material, set prices, and but Amazon is the first one I tried, and it works pretty well. And of course, maybe I'll stick with it because that's the one I know now. But
I had a colleague who
it does give you control. For example, I had submitted this to Springer, but there was months and they replied and so on. I published it myself, and then they said, "Yeah, we accept it," and so on. But I already published it myself, so.
Yes, and at least if it's on Amazon and if they've assigned an ISBN, then it's possible for academic bookstores and so forth to reference the book by that number.
Oh, by the way, it is in bookstores. You can easily find it on the internet just by type my name, Garret Sobczyk, on Amazon, and it'll come up right over. I can give you the address on that too.
Okay, great. I think you have my shared screen here at the moment. There's nothing much on here other than just to remind you that Dr. Santilli will be giving a lecture next week on November 3rd. We currently don't have lectures scheduled after that, so I'm still soliciting suggestions from anyone. I'm not sure, Jesus, maybe you would be interested in continuing with a presentation relating to your theory of interaction.
Okay.
I do have some questions that I perhaps could send to you if that would stimulate you to want to say more.
Okay. I love to speak more about this. Yes.
Okay, great. So maybe I can schedule you, say, for November 10. Is that...
Yeah, unfortunately, Dr. Page, remember I sent you an email some time ago that weekend I will be out of town for a travel, so I will be missing the lecture. I am sorry.
We starting on November 10?
And then, yes, I will be. I sent you an email a few weeks ago that
yes, I recall.
Was scheduled a long time ago. I couldn't reschedule it, but I'll be back in on the subsequent Wednesday. I'll be in.
Okay. I mean, we could, of course, just decide to suspend for a period of time. Originally, we were thinking about doing this every 2 weeks, but that has started to seem like a little bit too long between seminars. So anyway, we can communicate by email if you have any other suggestions. But for now, let's say November 10, and of course there'll be a recording of the presentation. So if you aren't able to be there on the 10th, you can certainly watch the recording later. And so with that, sorry, Jesus.
Okay, or for this. Maybe we can defer 1 week. I don't know if for Professor Santilli's okay.
Yes, the following week on the 10th will be yes, yes. subsequent Wednesday, I will be available. Yeah, I will
November
miss. I will
17th.
miss the meeting on. I am unavailable the entire week of around the 10th of November, but the following week I am available. Well,
Okay, then.
Professor Cruz, maybe you will have extra time, extra days to prepare your lecture. It's not that bad, perhaps, for you.
Yes, yes, it is better for me too.
Yes.
Yes. Okay,
Yes.
great. Then that's what we'll do. Okay, so other than that, I'd like to introduce someone everybody everybody knows already. I'm looking forward to hearing what Dr. Sobczyk has to say about Hestenes' approach to relativity, and particularly since it seems to overlap, at least in some respects, with what Oscillation was doing, although in a different formalism. So I think this should be very interesting. So please carry on. I'll just stop my share screen, and you can
Okay,
go
well,
ahead
thank
and
you very much.
set
And
it up.
I'm certainly very happy to present my talk. In fact, I will share the book with anyone that asked for it, that maybe can't attend today. If they write me an email, I would requesting me to, I'll just send them the electronic version. Of course, the other version is in Amazon.com. It can be found very easily under my name. Okay, so I can share screen now, I suppose, right?
Yes, you should be able to.
Okay, let's try it. Okay, if I can. Okay, let's see how this is going to work here. Okay, I don't want this. Nor do I want this. Okay, it's telling me to share. Let's
Yes,
see.
at the bottom of the screen, you should see. Oh yes, okay. That looks good.
Okay, I guess I'm all right now.
Yes.
Okay, so let me. So is that pretty clear?
Yes,
Yes,
yes, we can.
that's fine for me.
Okay, so again, I start with Hestenes' quote, "Algebra without geometry is blind. Geometry without algebra is dumb." D. Hestenes. Well, we have that in my book with Hestenes. You can find that quote. And then I ask a question: can a geometry be invented that gives insight into category theory? Maybe one of you could answer that question, because I really believe that I know Zbyszek's point of view was that everything should be done with algebra, but I really believe that you do need geometry, some type of geometry, to focus attention on the algebra to give insight into where it's going. Algebra itself is just a bunch of rules. And geometry, for example, the rules are very definite. And well, in particular, geometric algebra, I look upon it as the completion of the real number system to include the notion of direction. So basically, in my talk today, I'd like to, basically, it's an introduction to my book, Matrix Gateway to Geometric Algebra. The chapter I'll be talking mostly about is chapter 7. So let me get another reference that you might be interested in is this one here at the bottom. Well, it's called Conformal Mappings in Geometric Algebra, which was published in the notices of the American Mathematical Society, number 3. So that would be a very useful reference too, I think, on this.
Garret, I have one question. Would you be able to send us a copy of your slides later?
Okay.
Well, I know I noticed you have an embedded link there. That was what prompted me to ask. So.
I can certainly send a copy of this page. That's right. It's just a single page.
Yeah, or just an email with that the link to the.
Well, also I can attach the book, the electronic version of the book to that. That's really the basic reference. I'll be taking most of my pictures and slides from that book right now. So, but then I'll just send that along with this title page here. That's
also the paper conformal mappings.
Yes, yeah, that actually is right. I could click on it and go to it right now. That's actually an activated click. So the notice publishes that on their website, but it's free, so it doesn't cost anything.
Great.
Okay, so let me go to the next. Let's see if I can do that here. Okay, I'm going to go to the next one. So let's look at this one. So this could, nope, I don't want that one. Let me close that. What I want is, okay, I want to get out of this too. Okay, I gotta. Okay, what I want is. Okay, let's start with this one right here. Okay. So this is really the preface of the book. I won't spend much time on it because it is in the preface of the book, but it gives an overall view of what's in the book. In particular, I'm interested in showing how matrix algebra is very intimately connected to geometric algebra, in that it can be, it's a matrix representation of geometric algebra. So the basic chapters are, chapter 1 introduces the hyperbolic numbers alongside familiar complex numbers. At the heart of complex numbers is so-called unit imaginary I squared equal to -1. In contrast, the hyperbolic numbers are based on the introduction of a new square root of +1, which I called here a unipotent. I'm not sure I like that name so much. The hyperbolic numbers can be applied to solving the cubic equation and applied to Lorentzian geometry of relativity theory, which I'll talk about a little more today. Okay, so chapter 2 is just a basic review of vectors as directed line segments and the generalization of bivectors and so on that are in geometric algebra. Addition, and I might just mention this chapter 2 was written in along with 2 engineers from Volkswagen in Mexico who were very interested, had contacted me, and we wrote this paper including, so it's a very basic introduction to the geometric algebra of G3, of space. So I recommend that highly for an introductory chapter to geometric algebra. Okay, chapter 4 undertakes a more standard classification of all geometric algebras and their basic properties. By the geometrization of the real number system, we mean the extension of the real number system to include an arbitrary number of new anti-commuting square roots of plus and minus 1. So it seems to me that that is a very natural extension of the real and complex numbers, because you can see how all these different number systems fits in. In fact, I would not be surprised whether Dr. Santilli's isotopic Lie algebras must be somehow closely related. Just the relationship we write down reminds me of some of the things in geometric algebra. So it might be interesting to explore what I think must be a close relationship between the 2 ways of formalisms.
Oh, I agree. Yes, indeed. Yes.
Okay, so going on, chapter 5, continuation of the work begun in chapter 3, concept of a geometric matrix is extended to higher dimensional square matrices by introducing what I call the directed Kronecker product of matrices. So in other words, the whole idea of the book is to bring geometric algebra very, very close to matrices. And in fact, you can consider matrices are the coordinates of a geometric algebra, nothing more, nothing less. It's just the geometry behind matrices, which is, well, that fulfills the matrices is matrix algebra, and the geometry, it really is geometric algebra. So that's a theme I've been talking about for 50 years, and Hestenes for what, 60 or 70 years. And
Garret,
slowly it's
can I ask you a question at this point?
Okay.
About how you would define geometry. Like what do you mean when you say geometry?
Well, geometry of Euclidean space, geometry of Lorentzian space, geometry of higher dimensional spaces.
So you take it as something that we understand intuitively, as a
well, I take it as a language which gives you an intuitive understanding of the well, like I say, you start with real numbers. It was extended historically to the complex numbers. And then you had what, the Quaternions, and then you had Clifford, geometric algebra. He's the one that introduced the term geometric algebra, which I think is the most.
But up to the point where you said geometric algebra, the motivations seemed primarily algebraic, although the applications of something like Quaternions certainly seemed to be appropriate for what we would intuitively call geometry.
Okay, of course, that's a whole another question of, Hamilton invented the Quaternions. He thought about the Quaternions as being vectors, which have square minus 1, or the basis anti-commuting. So this is the whole idea that if we give up in the real number system, we give up the commutative law of multiplication, we can stick geometry in an arbitrary number of dimensions as vectors which are orthogonal. Orthogonal vectors anti-commute. Orthogonal vectors, a vector has either plus square or minus square. So depending upon whether it's well, that's why I study hyperbolic number plane, which I actually started writing when I was at when Professor Keller invited me to FES Qualtitlan Iscali. That was a paper I began there and finished it really at the university. But that's the whole idea of the paper, was to show you by introducing a new number into the real number system, which has square plus 1, but which is not equal to plus or minus 1, then you have what I call the hyperbolic numbers. Well, that's not the same as hyperbolic geometry. That other people use the word a little differently, but I think it's an appropriate use because a hyperbolic number plane consists of the hyperbolus x squared plus or minus y squared is equal to 1, and so instead of the circle plane, which was later taken over by the complex numbers, you have the hyperbolic number plane. So I would very recommend the hyperbolic number plane as also to get people, it was difficult for people to accept the idea of a complex number, I squared equals to minus 1. But eventually what they did is they put geometry into it. You have the complex number plane just as you have the real number plane. So you can, in the plane, you can either name points by a pair of coordinates, or you can name points by a complex number. And then Hamilton did the same thing with 3-dimensional space with the Quaternions. Well, Clifford did the same thing for an arbitrary number of dimensions of spaces of arbitrary signature. So this is the basic idea of geometric algebra. It's a natural extension of the real number system to include new anti-commuting square roots of plus and minus 1, which are not the real numbers and which are not complex numbers, but the generalization to any number of dimensions. To me,
But-
this is very beautiful.
Well, it's very compelling, but also I still have some difficulty conceptually associating the square root of unity with the concept of direction. You know, that although I understand, of course, as you mentioned, like the model that was produced that showed when we talk about complex numbers, we can talk about them in a plane. And then the concept of dimensions sort of arises when you want to look for a model of what the square root of -1 might be, right? So a unit vector in some other direction. Right? But square root as an operation, algebraic operation, doesn't make me think of direction immediately. The alternative, like, would be when one starts with something like a number field, and then consider, for example, functions over the number field forming an algebra, and then looking at derivations of those functions, right? So then you have naturally associated a direction with a derivative. Right?
Okay,
So
let me
that
break
sort
it
of makes
there.
sense, but I don't know quite how to do the same thing when I'm looking at roots of unity. Right?
Okay, well, that's very interesting what you're saying, because in my talk that I gave at the memorial, you know, at Zbyszek's memorial, I touched upon some of those ideas where you're using, well, in fact, that this paper I'm trying to complete from November for the book that will be published in memory of Zbyszek. It'll relate to these ideas, but that's right. You can talk about a direction as a directional derivative, okay, or a partial with respect to a coordinate, but you're missing geometry when you do that. And of course, I doubt for many years thinking about the same ideas, but actually mentally you're free to, for example, you're free to associate that with the complex imaginary axis. So look, you can take the real number plane, okay? So that's what Descartes did. A point corresponds to a pair of coordinates. Okay, then you go to the complex plane. Well, that where you're associating the imaginary axis with real axis is the real axis still. Okay, but then you go to, okay, let's not talk about quaternions. We'll skip over quaternions. But then you go to the hyperbolic number plane. What is a hyperbolic number plane? That's where you take a new square root of +1. That's what stops people. They say, why do you want to take a new square root of +1? You have +1 and -1. You already have two square roots of +1, +1 and -1. But that's an idea that's missing. That's an idea that must be included in order to properly understand geometric algebra. So then you have the hyperbolic number plane, where you have the real numbers along the real axis, and you have a hyperbolic number u, which is not equal to ±1, which is along the y-axis. Okay, so that's the hyperbolic number plane. Also, Clifford algebra, CL1, where I call it the geometric algebra generated by one unit vector, which is not the same thing as the real numbers because it's a new square root of +1. You can interpret it algebraically as being a new square root of +1, and that paper was also published in the College Mathematics Journal. Also, I guess that one might cost money, but I can. Well, also, by the way, it's the first chapter of this book here, so that paper is also in this Matrix Gateway books, which I'm going to send you. So those are two important chapters. Well, I can go back up on the.
Thanks.
Okay, so chapter 1 introduces hyperbolic numbers alongside familiar geometric complex numbers at the heart of the complex so-called unit imaginary I equals square. In contrast, the hyperbolic numbers are based on introducing a new square root of +1. Well, I call it a unipotent, but you can call it just a unit vector, which has square plus 1. It's just a vector. In particular, we identify it with the y-axis. So it's exactly the same idea as complex numbers. There's no reason why you cannot name the points in the plane, real number plane, with a complex number, or you can name it with a pair of real numbers, or you can name it with a hyperbolic number, or you know this, or you name it with anything you want. You're only limited by your imagination. Okay, so let me go on here. Okay, so chapter 4. So this gives you a more overview of all of geometric algebra and its relationship to higher dimensional geometric algebras. Well, you're really inventing a geometric interpretation of the geometric quantities in Rn. Well, that's the Euclidean space, where coordinate-wise, Rn is just n real numbers in a coordinate system. You're assigned. That's the Descartes way of looking at things, which is extremely important. In matrix theory, you have a vector as a column vector. Well, in geometric algebra, you're interpreting a vector as actually a matrix. Well, the Pauli matrices, for example, well, that's another thing that stopped physicists, I guess, from looking at geometric algebra. They think about a Pauli matrix, they call them, well, you know, the standard three Pauli matrices. They don't, we just interpret them as vectors, and you're free to do that. But I guess physicists might look at that a little differently. Anyway, so let me go on.
Well, I don't have any difficulty really at all thinking of a matrix as a vector in the sense of forming a basis for a vector space, for example. So that seems straightforward, provided that you define, first of all, what you mean by vector space, I suppose.
Okay, well, let me go on, and I want to actually show you how in space-time algebra, you have for example, I don't think a metric is so, I think a metric is not, Zbyszek, you know, he's always, or, you know, these people, you people, if you want, are always talking about vectors and covectors. It's true, you can always introduce, you know, a covector is actually a real valued function on vectors, okay? But you don't have to thought of that way. There are other ways of thinking about covectors, and that okay, so let me go on, and I'll get along to talking about some more of these ideas here. But I don't think we should be so rigid in our way of thinking of a metric and associating a metric is not such a rigid system, I think, as, okay, you can say covector.
Well, that was maybe one of my motivations for asking you for a definition of geometry, right? Because many people would say that geometry implies metric, or maybe even the other way around.
Well, no. Look, Grassmann algebra is metric free, and people don't think about Grassmann algebra as tying up a metric. But let me go on, because I want to talk about exactly that might help you understand these things. So
that's great.
Well, I think, okay, let me go on then. Okay, so what do I mean when I say geometry? Okay, I mean, geometry means vectors. Okay, everyone is clear what a vector is, a directed line system. But then you have bivectors. A bivector is like a vector, except it defines the direction of a plane segment. Okay, so you have unit vectors, you have unit bivectors. A unit bivector represents the direction of a plane. Okay, also, just like a vector, you can have a Lorentz vector, which has square -1, or a Euclidean vector, which has square +1, or you can also have bivectors. Euclidean bivectors have square -1, whereas, well, if you want to call them Lorentz bivectors, have square +1. So let me talk about, I'll show you how. So anyway, so what is what is geometry for me? Geometry geometrically consists of, well, you have scalars, which are real numbers or magnitudes. Then you have vectors, you have bivectors, you have trivectors, like the unit trivector of space has square minus 1. And then you have unit 4 vectors, unit 5 vectors, unit any number of vectors that you want. You can also consider that as Grossman algebra. Grossman algebra has vectors, bivectors, 2 vectors, 3 vectors, 4 vectors, 5, n vectors. Now okay, so the only thing, the difference between geometric algebra and Grossman algebra is that you're assigning a metric, okay? But the metric idea is not so fixed as you might think it is. So let me go on and I'll try to, okay, so the main chapter I want to emphasize, since I'm talking about special relativity, is chapter 7, basically. So let me go to, so here are my acknowledgements to the book here. Okay, so here are the contents here. Okay, so real hyperbolic numbers. So I suggest to get you started on geometric algebra, look at the hyperbolic numbers, the hyperbolic number plane alongside the complex number plane. It's a natural. And the interesting thing about the hyperbolic numbers is you can prove the solutions of cubic. You remember the solutions of cubic equation, which is algebra, pure algebra, only became possible with the introduction of the complex numbers. Well, actually, in this hyperbolic number paper, or this first chapter, which was also published in the College Mathematics Journal, you can solve cubic equations using the hyperbolic numbers. So if people had used the hyperbolic numbers instead of the complex numbers, it would have been equally forceful in getting people to accept hyperbolic numbers as being valid, because you can solve a cubic equation. Also, again, that's where you're putting geometry into algebra. Okay.
So you say it's kind of an accident that algebraists decided to use complex numbers for this particular problem.
Exactly. Well, you could say people were refused. They didn't even want to consider the square root of -1 because that was.
Well, but all they,
that's
you
where
were
the
arguing is.
Imaginary.
You were arguing, yes, yeah. So your argument is that it would have been easier if they had just been allowed themselves to think of the square root, another square root of 1.
Well, that's right. Well, that has to come later because, first of all, they called imaginary numbers imaginary because they thought. But the fact of the matter is, real numbers also only exist in your mind. They don't really exist any more than a model. So that's all we're talking about. So algebra really is a construction of the mind. And I claim, well, the geometry should be put into it because it helps our and not just pure rules from algebra. Okay, anyway. So, okay, from vectors to geometric. This is a very important chapter from an elementary point of view, which was written by me with the help of, well, my co-authors were 2 Volkswagen engineers from the Volkswagen in Puebla, Mexico, which is interesting because they became fascinated with. It's interesting that computer scientists really have picked up geometric algebra, as evidenced by. But you have theoretical physicists, named the Cambridge group, picked it up after our book was published in 1985. There's a famous picture of them studying geometric algebra from our book, that they read it from cover to cover. And that's what motivated them to go on. By the way, they invited me to Cambridge University at the same time, and I had a very enjoyable week with them talking about these ideas in Cambridge. And of course, the first geometric algebra conference was organized with Professor Chisholm, who had visited us in Clemson, South Carolina. And he had asked me whether I thought it was a good idea to have a Clifford Algebra conference, which I, of course, thought it was a great idea. So because of the work of the Cambridge group, Chisholm got interested in it as well. Professor Chisholm from So that goes into the history. I won't talk more about the history right now. Okay, so of course the book, the physics book by Lazenby and Doran and Gall, well, actually it's just Lazenby and Doran, has achieved some recognition in the physics community, although it's still, I don't think it's universally adapted by in any means, since not all physicists are aware of that book, the books by, but they also, okay, well, let me go on.
It's sort of unfortunate that that group somewhat was basically, well, they just self-disbanded and went on to apply geometric algebra concepts in very applied engineering applications, as I understand it.
No, not really. Lazenby, that's right. He's an astrophysicist, I guess. But Hestenes thought was the most important ideas from Lazenby, Doran, and Stephen Gall was their invention of so-called flat space-time general relativity. I started studying that, but had some questions and got distracted into other things. But Hestenes believes that that's extremely important. He's written about it himself. A number of papers by Hestenes addressing the same ideas. I don't want to talk about those ideas right now, but certainly Lazenby, that's right. His wife is an engineer, and she's also adapted geometric algebra for the engineers, and they've picked it up. Computer scientists have picked it up. Doran has also gone, has a company, I guess, using geometric algebra for, well, but it goes, anyway, it seems to me that more engineers have picked it up faster than advanced mathematicians. They you know, okay, they're busy solving the four-color problem, Fermat's last theorem. You know, that's what, well, then you have string. Anyway, somehow geometric algebra is not seen, as I look at it, as a very basic concept of the real number system. And it should be addressed that way. And I'm extremely frustrated, you might call it, after 50 years. Well, it's making some progress, but still it's not in the mainstream. Well, that's why I wrote the article for the notices. I thought that might encourage, but well, I've got positive reviews for it, but again, it's not, I don't see geometric algebra as being mainstream yet, which I think it should be. Okay, so let's see how much time. Okay, let me go on then and open the actual manuscript, well, the book material. So let me get out of this thing here. Okay. So I want to open the book now. So I need to get out of this screen. Okay, so here's the manuscript for the book. Well, here's the electronic version of the book. Okay, Matrix Gateway to Geometric Algebra. Okay, so let me go down here. So I'm going to go to page Spinners, page 107. Okay, I can get rid of this. I don't need this here. Okay, let's go to page 107. Three. So I'd like to talk about the hyperbolic number plane, the first chapter, but I want to concentrate on special relativity since that's how I advertised the talk. But I never really have given a talk about this book, really, or did I? Maybe I did, I can't remember. Okay, so let's start with this chapter here. Okay, 7.2. Okay, so that's chapter 7. So again, I will send you the book after we get offline, but I will go through it now. Okay, so let's start with the geometric algebra G3. So what is it? Well, geometric algebra G3, the basis of that, it's spanned by the real numbers. Okay, 1 generating the real numbers over the geometric algebra G3 is over the real number system. Okay, so the scalars are the real numbers. Okay, so I consider it to be the extension of the real number system to include 3 new square roots of +1, which are anti-commuting. So you have E1 along the x-axis, E2 along the y-axis, and E3 along the z-axis. Now, in addition, you have the unit bivectors. Well, the unit bivector of the xy plane is denoted by E1, 2. Remember that E1, E2, and E3 are anti-commutative. They have square roots of +1, and they're anti-commutative. E1 times E2 is equal to minus, whether they have Ej times Ek is equal to minus Ek times Ej. The unit bivector in the xy plane, this is in the xz plane, and this is in the yz plane. Okay, I hope I'm still online. I have a message that's stable. Okay, so the
There's a
even
little
vector,
bit of delay in your voice sometimes, but otherwise you're still coming through fine.
okay,
Yes,
I might have to restart the hotspot or something.
there is a resonance sometime, but not all the time. It's okay. We can understand.
Okay.
At
Yes,
least
it's
I can
clear.
understand.
Okay, so here you have the basis of the geometric algebra consisting of 3 unit vectors along the x, y, z axis, 3 bivectors, E1, 2, E1, 3, E2, 3 along xy plane, xz plane, and yz plane, and 1 trivector that represents a unit volume element. Now, if you use the rules, you can easily calculate that if you square E1, 2, 3, you get -1. So the fact of the matter is, there's many different interpretations of the square root of -1. We have the imaginary number I with complex scalars. Well, you're not associating any geometric idea with that, but that doesn't mean you can't associate a vector with, as Hamilton's quaternion, they associated vectors with quaternions. So you're free, you're mentally free to associate anything with the square root of -1 that you want to. For the complex number plane, you associate the y-axis with square root of -1. Just so you can associate for the hyperbolic numbers plane, you associate 1 vector, call it E1, with the y-axis, and then the real numbers as the real axis. Okay. So the interesting thing about the hyperbolic numbers is that when you look at, well, I call it the unipotent, plus, if you take 1 plus or minus E3, and you square that quantity, you get an idempotent. Well, for complex numbers, you don't have any idempotency. Well, yeah, you do have 2 idempotents. 0 squared is equal to 0, and 1 squared is equal to 1 for complex numbers. For the hyperbolic numbers, you have any more. Well, you have the 2 asymptotes of the hyperbolas, x squared plus or minus y squared equal to 1, or y squared plus or minus x squared equal to 1. That's the 4 branches. Any vector along the asymptotes are idempotents. Well, or the unit idempotent has our projections, u squared, and so on. So, but notice that if you take u plus minus u minus, you get E3. So that, okay. So again,
doesn't that seem a little anomalous? That
what do you mean? Anomalous.
Oh, I see. Oh no, sorry. U is defined in terms of E3, an idempotent.
Right. So again, if you're thinking about the hyperbolic number plane, 1 is on the real axis, and E3 is along the y-axis. So you see, you're at the point 1, 1 in the xy plane, and that's represented by u plus and 1 minus E3. Well, that's in the 4th quadrant of the real number plane. Then,
so clearly you have at least 2 other idempotents. I mean,
any vector on the asymptotes of the hyperbola are nilpotents. They have square 0. Okay. Well, okay, that's different. then you have to go to the, you have to say a little more to see that. But
1 plus or minus E2 is also an idempotent, and 1 plus
that's
or
right.
minus
But
E1 is
notice
also an
that,
idempotent.
notice that they're mutually annihilating idempotent. If you multiply U plus times U minus, you get 0. So you have divisors of 0 in the hyperbolic number plane, which you don't have in the real number plane, which you don't have in the complex number plane. But that's the richness of the hyperbolic plane, which is missing in the complex number plane. You might look at it that way, as in fact.
Yeah,
as
that's
I
a nice
say,
way of
you can
looking. Yes, yes, indeed. Yeah.
Okay, so let's go on because I don't want to run too much over time here. Okay, I'm doing all right.
Yeah, you're
Okay,
still
so
all
here
right.
again, here's your geometry. Scalars, real numbers, vectors, and then you have vectors here, and then you have bivectors. Everything has a geometric interpretation. Now, there's other geometric notations you can give it, or like Clifford algebra community, they're not really interested. Why do you think they call it just Clifford algebra? They're only interested in the algebraic structure. I think that's a defect. I think that's missing something very important. Well, that's why you have a Clifford algebra community and a geometric algebra community. The Clifford algebra are really only interested in the algebraic structure for their, I guess you can say, functional analysis extended to higher dimensions by algebraically. Okay, so there's a geometric interpretation of all the algebraic numbers in the geometric algebra G3, scalars, vectors, bivectors, and a pseudoscalar or a trivector, E1 times E2 times E3. You square a bivector, Euclidean bivector, you have square minus 1. You square a trivector, you also have square minus 1. But notice that it's not, so Grossman always interpreted bivector as a plane segment, but you can also interpret it as any area in the plane. For example, this circle I, well, we call that U, I suppose. It shouldn't be I, since we call that. But what's important is the orientation. Notice the orientation of a bivector has two orientations. It's A, B, or B, A. Well, those vectors are anti-commutative. It's orthogonal. I think you can get the idea very quickly if you start with the basics. So chapter 1 and chapter 2. Okay, well, this is, I won't, okay, here you have the Pauli matrices. I'm not going to talk about this very well. This is we're using matrix notation here. You take a matrix with 1 E1, U plus 1 E1, and you get this quantity. This is the basis for the geometric algebra G3 in terms of matrices. So this ties together the matrix notation with allowing matrices to have geometric numbers as entries. But you have to remember the structure of the geometric algebra. E1 squared is equal to 1. E1 times E2 is equal to minus E2 times E1, and so on. Okay, so a general geometric number in G3 consists of a real number, y times I, where in this case, no, I is equal to the unit pseudoscalar, E1 times E2 times E3, plus A plus IB. So those are the most general geometric numbers, well, algebraic numbers in G3, which has a complete geometric interpretation. X is a real number part. Y is the the vector, the real number plus the trivector part. Notice that I will commute. It's in the center of the algebra. So we can interpret X plus I, Y as being a complex number. It has exactly the same characteristics of X plus I, Y, where I is interpreted as a square root of minus 1. But I, in this case, is a unit trivector. the product of E1 times E2 times E3. There it is right here. So E1 times E2 times E3 squared. It's very easy to show, you know, remember geometric algebra is associative, has the same rules of multiplication as matrices. So that also helps you remember the rules of geometric algebra, exactly equivalent to the rules of matrix algebra. So it's very easy to show that E1, 2, 3 squared is equal to -1. So we're not really talking about metrics all the time. A trivector, a unit trivector has square -1. Okay, you want to call that the metric on, you know, I think metric is overused and confused. But let me go on because I'd like to show you how a different way of looking at special relativity that people aren't aware of, that even Hestenes is not aware of. I introduced it to him. And Baylis, by the way, uses, William Baylis uses geometric algebra of space, G3, to do relativity theory. I've also written papers with Baylis on the subject, which can be found, which are referenced in this book as well. So I won't, well, these are interesting formulas which are made possible by geometric algebra. Important formula for the product of Lorentz boost of the form e to the hyperbolic angle phi1 times a unit vector a1 as this expression. Very interesting expression, not so trivial to calculate it, but here you can identify the product of two Lorentz boost is equal to this quantity here. It's a product of a hyperbolic e to the hyperbolic number here times e to the a bivector. I have to explain more about that, but I don't really want to do that because I'd like to talk about other ideas. So similarly, the product of two Euclidean rotations is found to be, okay, so these are representations of spinors as e to the I a1 hat. That defines, remember, I is the pseudoscalar, that's the unit trivector. So I times a hat, 1 hat, is equal to a unit bivector. So with an angle, a Euclidean angle, the product of these two gives you this then. Well, anyway, so these are just general formulas for, okay, stereographic projection, very important in geometric algebra, as it is in, again, I'm not going to talk about that, but it's in the book. So let's just keep going. Two component spinors. Okay, I spent a lot of time with spinors, but I don't want to talk about that. Let's keep going. I want to get to other things. Well, that's interesting, but I don't want to talk about that. Observers in the uncertainty principle. But let's keep going. Okay. Well, that's interesting, but I'm not going to talk about it. That was a model of neutrino oscillation. Two flavor states, blue and green. In the atmosphere, neutrinos lose one of their states. You know, it's basically 3 different flavors of neutrinos. But when it hits the atmosphere, it filters out. One of them doesn't occur so much. So I talk about that situation. Okay, space-time horizon of an observer. This is very important for what I wanted to say. So again,
just one comment. So you have introduced the concept of observer initially from the point of view of quantum mechanics. Is that correct?
well, no, observer I think about is just as you or me. we're observers, right? And we're observers in the same reference frame if not in relative, we have no velocity between, relative velocity between us. So an inertial system is all observers which have no velocity with respect to each other. So in particular, here we are in space, and we're all at our computers relative. We're not moving with respect to each other. We're moving on the Earth and all that, but we're in the same inertial system for special relativity because there's no, we're not traveling.
But
We're
your
not in the
previous
car
sec-
driving or anything. We're
your previous sections of this chapter were focused primarily on quantum mechanics. And although you said you didn't want to spend time talking about that.
okay. Well, I'll just.
I guess my main question was do you see this notion of observer as somehow unified between relativity and quantum mechanics by the use of geometric algebra?
Yes, I think that's right. In fact, well, a lot of quantum mechanics is done with geometric algebra and is continued to being done. But let me go on and I'll clear. Okay, here's a very important picture I want to talk about.
May I ask if you don't mind? I apologize. May I ask a little bit clarification regarding the inertial character? So is it correct to say that you assume that the relative velocity is zero, but nevertheless, this implies the possibility that the set of observer can be accelerated and therefore not be necessarily inertial? Could you please elaborate a little bit?
Oh, okay. This picture, I think, will explain some of those ideas right now.
Thank you.
The picture you have in front of you, let me interpret that picture for you in detail. Okay, so we're in the blue plane. We're all in the same inertial system via that blue plane, okay? That's a circle. Okay, and now look what I'm doing. If I go up by the angle phi, I guess I can, okay, good. Can you see my arrow?
Yes,
I
can.
arrow for you? Okay, so that's the angle that defines the velocity of two inertial systems. So the people in the yellow plane, if you were driving in your car, then you're in a different inertial system. Well, you're such minimal velocity, of course, it doesn't really matter. You can assume that you're still in the blue system, but in reality, that's not the case. And this can lead to confusion too, because Hestenes, in his talking about, uses the same conventions as Baylis does. In his, Baylis only uses geometric algebra G3 to do special relativity. He does not leave G3, and he's been pretty successful at selling. But again, he represents a Lorentz trend. The reason I wrote a paper with Baylis was because we had a different way of representing Lorentz transformations. But I want to explain why his representation you might call a passive. Okay, there's an active boost and a passive boost. So that's what the paper with Baylis is talking about. So Hestenes also adapted the passive transformation form of the Lorentz boost, where I'm adopting an active transformation. In other words, I am distinguishing, if you're in any relative motion with respect to observer, what you're doing is you're tipping your Euclidean. This is only two-dimensional, of course, because I can't represent the extra dimension, but the Euclidean space, you're defining a different Euclidean space for every inertial observer. So if observers are at rest, they're in the same inertial system denoted by this circle here, the blue circle. But if you're at half the speed of light, notice you're in a Euclidean system. You're using a different metric, right? But really you're in the same, the metric is not really so, you're assigning a metric for the Euclidean vectors in that inertial system. Well, here you have it, I represent. So now if you go to the light cone, then the idea of inertial system is not defined, okay? You have null vectors. But for any, you can go to the speed of light, almost the speed of light, and you have an inertial system for particles. Okay, so that's the viewpoint in G3. So the active viewpoint in G3. So Hestenes was amazed when I said a moving vector is not the same thing as a vector with no relative. In other words, I guess you can't see me, but I'm holding up a pen in my hand. It's a vector, just a vector.
I have optical as instrument, so I can see. Thank you.
Can you? Yeah. So anyway, here's a vector. Any vector in the blue plane as a two-dimension is an ordinary vector. But if you look at, if you take a vector in your hand and you move it out in a direction, it requires a bivector part. A bivector part has square minus 1. Anyway, let me. Okay, so this is a very important picture for understanding what I call an active boost. Okay, so but again, it's you have to look at it more closely. But let me go on here. So a very important figure, 7.5 here. You can study it later, maybe. Okay, now, let me talk about an event. Okay, a space-time event. What is an event? Well, for us in our inertial system, the blue frame, it consists of a time t, which we read on our watch, and a position vector, okay, from the origin, which I call x, an ordinary position vector. So the only difference between space-time, Newton space-time, and special relativity space-time is that is in this picture here. You're in a different relative plane. This plane here, the inertial system is moving with respect to this other one, but you have what is a unit vector in this yellow plane. When the first observer looks at it in the blue plane, he sees it as an electromagnetic wave. So electric field, that's a good way of looking at it. If you take an electric charge, if you look at it, if you're holding an electron in your hand, you just see an electric field. But now take that electron and move it. What do you see? You still see an electric field, but you also pick up a bivector for the magnetic field. So, but then if you take that vector and you walk with it, then you still only see an electric field. I think this is very important and what physicists do not stand to this day. Does anyone have a comment on that?
Well, let me bring up Dr. Santilli's point again, maybe in a slightly different way. I think he asked for a definition of inertial frame, I guess.
Yes.
Because you said in passing that we would say that something was inertial if the relative velocity was 0. But if we have say two observers accelerating, not inertial, they're both accelerating in the same way.
Okay.
Like then they have a relative velocity of 0, but we just said that they're accelerating.
Yes, in this case there are problems with, especially with the Lorentz boost and other issue. But I see no contradiction. In other words, it's mainly an additional condition that I see no contradiction on what you have stated. Only the clarification that not enough that in addition to the relative velocity being 0, that the set of all those observers is not accelerating. In other words, it is an additional condition in which everything you stated remains correct.
Well, that's right. If you're in a car that's going at 100 miles an hour, all the people in the car are in the same inertial system, whether it's accelerating or not accelerating. They're still, if they're at rest with respect to each other, they're in the same, whether it's accelerating or not accelerating, they're in the same inertial system.
That is correct, but the problem of the acceleration, to my recollection, I could be wrong, Dr. Garret. Then the problem may originate when you use that reference, that inertial reference frame, to examine events, events in the reality of the world. That's where the condition of that in addition to the relative velocity zero, that the set of observers not be accelerating, that I think may be recommendable, but has to be checked.
Okay. I'm actually going to say more about this, the point that you're making, when we go to the Minkowski plane, which is up next, which I want to spend at least a minute. I know we're okay. I guess I have a little time to.
Yeah,
but
there's still 20 minutes.
Let me show you how I think about acceleration then. Okay, so let's keep going.
It is a very intriguing point, because if we can incorporate acceleration, that life of Lorentz transformation is much easier and beautiful. Yeah.
Well, I think so. I think we can do it. Like I say, Baylis has developed special relativity in G3, the geometric algebra, which is an 8-dimensional space over the real number system. So, but let me show you how it's related. I think a very deep insight when you consider it in Minkowski space, which I'll define then as well. So let me go on. So again, this is really looking at it from everything from in the geometric algebra G3. So that's this X, a space-time event is named by a point, okay, capital X, CT plus X. So again, time is just what's on your watch. You're looking at your watch, it's ticking. A position vector is an ordinary position vector, nothing more, nothing less. Okay, let's go on now. Okay, well, I go through some of this. I'm not going to go through this because it's just showing how you get the usual formulas that everyone knows, which you can look at your own leisure. But I want to. Okay, so but this is it. So I'm really trying to develop here. I wrote an early paper in Poland when I was at the Institute of Theoretical Physics, showing how you can do special relativity only in terms of G3. Well, but that's why I got interested in Baylis's. He does the same thing, but again, he uses passive boost, as does Hestenes. And I like an active boost, where I showed you that figure denoting that. And I say, if you take an electron and you walk with it, you still see just a charge. But if another person takes that electron, moves it, then you see a magnetic field as well, which a magnetic field is defined by a plane. It's in a plane. So it's natural to put, you can see how it, okay. So here I'm defining how relationship between inertial systems, but I don't want to talk about this because it's much better to talk about it in the Lorentz, in the Minkowski space-time. And then you'll see how it's related then. It's just a trick to get it from Minkowski. Okay, so here's a nice picture of what I was talking about. So in the event horizon H, so what you have, H and H prime represent two inertial systems. This one is moving to the right, H prime. So you think about this one, X prime, as moving at a constant velocity with respect to X. So the question is, what is an electric? So if you take a charge, put a charge at TV, okay? So our charge is at TV. Of course, time is advancing. So again, you can think about we're moving through time as t advances in our system. The vector still is the same vector. It's at rest, but time is nevertheless, you can't stop time. Okay, but now, so these are just, so this is the green, this is the blue frame, and this is the yellow frame, okay? So here you have the guy walking in the yellow frame with his electric charge in his hand, and you question, how does that first observer see the electric charge? Well, he sees it as a magnetic field because it has a magnetic component as well. Okay, in H prime, the charge is located at the spatial origin and the electric field is observed at the point X prime. The time coordinates, okay, C and C prime. Well, again, that's why we have trouble. We don't have enough dimensions to note these things. That's why we need geometric algebra. Okay, so these are standard formulas that Biot-Savart law. So this shows you then deriving that from just considering that to be a moving frame, you get the representation that people know about and call Biot-Savart law for changing inertial systems. Okay, now I want to talk about the final topic will be Minkowski space-time to try to get you to understand how we look at that. Well, again, there's two views, passive and active. I'm using the active view here. Baylis and Hestenes use the passive, which is a different way of looking at Lorentz boost. Okay, so now I introduce a geometric algebra G13. What does that mean? Well, that means we're picking out new square roots of plus and minus 1. Okay, we're picking out one, which are anti-commutative vectors. So we call gamma 0 has square plus 1. Gamma 1, gamma 2, and gamma 3 all have square minus 1. So we call that the geometric algebra G1 comma 3. 1 representing the 1 unit vector, which has square plus 1, and the other vectors have square minus 1. Okay, so these gamma vectors are mutually anti-commutative. So that's why I'm saying we're extending the real number system with 3 new square roots of plus and minus 1, which are anti-commutative. That makes it much more easy to interpret them as vectors then. So you're free to interpret a vector as whatever, okay. Okay, so they're anti-commutative, meaning gamma mu times v nu to minus mu not equal to nu. 2, 3. Okay, I had a message unstable. Can you still see me?
You're still here. A little bit of the audio was broken up a little bit. But...
Okay. Okay. So again, I'm assuming that we're extending the real number system by 4 vectors then, gamma 0, 1, 2, and 3, which are anti-commutative. Natural, it seems to me, that's just the extended real number system, simple as that, with geometric interpretations to everything. Okay, so now let's look what we have here. Noting that a vector v in the space of an observer with the ticking of the local clock is swept out as a bivector in space-time, we factor the space vector v, which was from our other algebra, into the space-time bivector, v wedge gamma 0 in Minkowski space-time. Each local inertial system corresponds to a unique timelike vector gamma 0. So in other words, okay, thus the local inertial system EK, which is equal to gamma k times gamma 0, k equal to 1, 2, 3, is related to the local inertial system E prime k by the mapping 7.51. Okay, so that's a Lorentz boost. So again, this is now at the level of the Minkowski space. Do I give the, maybe I'm missing one important formula, which I'd like to have.
That you already showed before, yes.
Okay. Oh, okay, here's a formula I wanted to show you. Okay, so look at it. Okay, so again, the main idea is that each inertial system is characterized by a unit timelike vector gamma 0. So if you have 2 observers in different reference frames, that means you have two different unit vectors which have a hyperbolic angle between them. You can map one to the other with a Lorentz boost. That's at the Dirac space level. Okay, and now I can relate that to a space-time event in G3 by this famous decomposition that Hestenes first wrote down, I believe, where that's my capital X from before. I write that as, a Dirac vector is simply a space-time vector, or Minkowski vector is just x0 times gamma 0 plus x1 times gamma 1 times x2 gamma 2, x3 gamma 3. Okay, now what I'm doing here. So in Clifford algebra, x times gamma 0 can always be decomposed into a dot product, gamma 0 dot x and gamma 0 wedge x. So we identify the dot product as CT for that observer. So that's us. We're not in relative motion to each other, plus a position vector, x wedge gamma 0. So you see a position vector in our space in our inertial system at the level of the Minkowski space.
That's a very nice rendering of this the basic notion. Yes, thank you.
Well, I would hope that we can discover a relationship between isotopic that you introduced. I think there must be some relationship.
Yes,
actually,
indeed.
thinking about it more and more, but I don't know what it is. Well, I'm looking forward to when you give your next talk. Is it?
It starts from your very first initial statement regarding the addition or the completion of the field of complex number, real complex, and then you go to the hyperbolic. Basically, all this type of completion can be identically or equivalently reformulated as isofield. So there is a very deep connection indeed.
So that would be, I think that would be great if we could do something with. So I think basically we just need to understand each other better.
Oh yes, indeed.
As usual.
My dream, the hope is that perhaps with isotopy we can simplify things, because that's what we do. That's why we have done it. You know, nonlinear interaction are turned into isolinear, which namely seems to be linear. So is the simplification in which we are interested, if it is there.
Okay, so this is a very important formula of what I wanted to say then, because it relates X in our ordinary inertial system that we're all in, because we're not in relative motion, to gamma 0. So you see gamma 0 completely defines our inertial system, defines the time, CT, and it defines the position vector, which is a bivector at the level of Minkowski space. So if you take a second gamma 0 prime, then you get CT prime plus X prime. But a vector in that system is not a vector in the first system. They're different. That's an act. So this is really an active transformation. I don't know why Hestenes, when he defined it, anyway, I don't want to talk about Hestenes here.
But that is exactly the same definition used by Oshevich, for example. That what you call gamma 0 here is the time-like vector that he would associate with a massive object of some sort.
But he doesn't interpret the position vector as gamma X wedge gamma 0, does he? I don't think he does, because he only uses
there is a formula very much like that. The mathematics is somewhat different, but the idea that you can that you can decompose something into a subalgebra. You can decompose something. You can map the algebra associated with Minkowski into an algebra associated with space, and another algebra associated with time. So there are two different maps, and these algebra maps that are defined by Oshevich are very much like the idempotes that you are referring to earlier in the paper. But they play a similar role with respect to decomposing something.
Yeah, but the only thing that stopped me with
I'd like to make
go ahead, please.
one comment. In the presentation that I made in the conference, I put one formula used by Zbigniew with the definition of observer, and then there is one part that is a projection, and the other part is a map. And I think that here you have these two, one projection and one map in this formula. Then I think that it's too much similar to that that Professor Osiewicz was using, yes. Because when we define the observer in this way, then after he described all the physical quantities in terms of that definition of observer, that is the definition of one reference frame. Then I think that we can find many similarities between them.
Okay,
yes.
let me just say to that comment that what stopped me, I had many arguments with Sobczyk about these ideas, was he insisted upon looking at things as vectors and covectors. But I think that idea, if you strictly follow that, that's where he had trouble with this thing I'm writing down right now. I think you can relate it to what you're saying. In fact, we have to look at it more closely. It'd be nice to do that. In fact, maybe we can all get together and write some joint paper relating all these ideas. But the other thing is that I think that Bill mentioned was the idea of interpreting a vector as a partial derivative, a direction of a partial derivative. I'm going to talk about this paper I'm writing for the proceedings of our conference. Will address those ideas and show you an operator approach, which in my book with Hestenes, the last page is actually devoted to Lie algebra using bivectors. But there's another approach to Lie algebra, which I think that which should have been covered in our book, but which I'm just now looking at now, and that's the operator approach, which is used by this main reference to my talk there. So I'll be able to improve it tremendously, and I think it'll make a big step to answering all these questions. You know, that was a stopping point, even for me. People did not want to identify a physical vector with a tangent space of a curved manifold. Terrible confusion, because people only wanted to look at a vector as a directional derivative or an operator. Well, that's fine, but that's another way of looking at it. However, they're all just representations of the idea that we're talking about. I hope I'm making sense.
I think so. I mean, Oshevich has a statement somewhere in one of the papers that he has a list of about 6 things that he calls synonyms, and so that he has about 6 different synonyms for the word vector. So one of them is derivation, right? And one of them, of course,
exactly. So that's really an operator interpretation of a vector, a derivation. Well, that's really a property of a partial derivative or a directional derivative. So those things I will address in my improved. I have a preprint I published, but what I can do now is much better. I've been working on it very hard. I can improve it tremendously, and I will improve it.
I look forward to actually having a chance to hear you discuss it in more detail, hopefully at a future meeting here.
Okay, well, so basically, okay, so then here we have the page we're looking at now. You can see the Dell inversion. That's just the gradient operator in four-dimensional space. And you can relate it to, so each observer has a distinct nabla operator, a gradient operator. But again, I think one of the things that are preventing communications between, I'm very happy that Sobczyk, that I was invited to be a speaker in this call. It surprised me really, because we did have trouble with Sobczyk communicating, because we seem to have a different view of vectors, and I was very pleased to be able to participate as a keynote speaker in the conference. Deeply appreciate it.
I think it's it was certainly appropriate, since I think Sobczyk would agree that science is not about agreement. It's fundamentally about disagreement, and that if you're agreeing, you're not really doing science. Right? It's when you're dealing with disagreements in great detail and in with great precision that you're actually doing science.
Well, that's right. But the problem with that is that there's a Clifford analysis community and a geometric algebra community. And why is there a distinction? Because basically there's agreements are seen to be so divisive that they stop considering the other one's point of view.
It's a pity.
Yeah, disagreement is also the essential for the so-called scientific process.
Yes.
Theoretically, a theory should be perfect when all disagreements are resolved, but this, so far it's still, I don't think there's been any theories to date that verified this requirement.
Yes.
So we're coming up on an hour and a half. Was there something in particular that you wanted to conclude with, Garret?
I think it's a pretty good place. Let's see, I can't, a pretty good place to stop. I did want to talk about, so again, at the level of Minkowski space, each inertial system is just a unit like time-like vector, gamma zero. So, okay, so if you have an accelerated frame, you're just rotating that vector, it has a velocity, accelerated frame is you're moving to a different inertial system. So you're moving along your time-like curve. It's not a straight line any longer. It's a curve. But you don't go to the asymptote, because that's the hyperbola that represents the speed of light. So there's no accelerated frames. Accelerated frames, you're just considering a time-like Minkowski vector that's moving along the time-like curve, which is not a straight line, which is for an inertial system in your space-time diagram.
Okay. Were there any other questions?
Okay, well, Maxwell's equation. So hop vibration, whatever. But okay, so thank you I appreciate the opportunity to speak.
I have a question, a very, very naive question, just to clear my mind. Could you please remind me, and I apologize for my ignorance, remind me the very, very definition of this hyperbolic, the birth of the hyperbolic, this new notion of a new square root of -1, the hyperbolic viewpoint.
Okay, so I'm going back to chapter 1 here. Let's see if I can find it here.
Because I want to be, I'm afraid I have some ambiguity in my mind. I want to clarify them.
Okay, let's just go to chapter 1 here. There it is. Okay, so what is a hyperbolic number plane? Well, it consists of the x-axis.
Sorry if I interrupt you, but before the plane, to understand the numbers, the hyperbolic numbers.
Okay, so here it is in a picture. x is the real axis, and u, that's the new square root of +1. U squared is equal to +1. But u is not equal to plus or minus 1. It's a new number, just as I is a new number. You consider it to be a new number, which is not a real number. So it's not equal to plus or minus 1, but it has square 1.
Okay, now I see the degree of freedom. Thank you clarifying this point. Yes, indeed. Yeah.
Very important point, because that
Yes,
all of geometric
fundamental.
algebra is built on new square roots of +1, which represent different directions in space.
Absolutely. That's why I ask. This is the fundamental, but that's a very, very pivot on which the whole theory is constructed essentially. Again, there are hidden degrees of freedom in the notion of square root. Yeah.
But in the case of the ISO numbers, if I understand correctly, generally speaking, you're considering new units.
Yes.
Whereas here, Garret is talking about new roots of a unique unit.
Well, but a unit, you can call them units too. They're units in, well, like here we're using it for the direction of the y-axis. U squared equal to +1.
Yeah.
Each root is a unit. Each root of unit is a unit.
That's right.
Yes.
Yes. I see.
My understanding, the hyperbolic numbers are another realization of the axiom of a numeric field.
Well, no, it's not a field because it has divisors of 0.
I'm sorry?
It has divisors of 0, like u plus times u minus, the idempotents are equal to 0. Any vector on the
now I see. So you do not verify the axiom of a field.
Well, it's not a field. It's not a field because you have idempotents. Well, you know,
that's what I wanted to clarify in my mind.
So that obviously must be the relationship between your ISO numbers, and you're not identifying you don't have numbers which have square +1, which are not real numbers, right?
Yeah. Yes, there is a possibility. I have to look at, honestly, there is a possibility of reformulating the hyperbolic number as iso numbers with the ordinary multiplication, verifying all the axiom of a field. In this case, I believe that your formulation will acquire much bigger structure and consistency. But
well, actually, we've already extended. I'm sure we're doing the same thing, but we're just looking at it differently. If you can put them together, then all the knowledge that has been published with your ISO numbers can be combined with everything in geometric algebra.
That's true, but the primary, let's remember the primary emphasis, the primary drive for to construct the ISO number is essentially to make them applicable, to make it usable in experiments, so that you can work out a theory, and the theory has to be, if you want to experiment, you have to formulate the numbers on a field, necessarily on a field. If you do not have the axiom of a field, then to my understanding, I could be wrong, but
okay. Let me just say one thing about that. You almost have a field. Only those points on the asymptotes instead of just having 0, you can't divide by 0. You can't divide by any number on the asymptotes of the hyperbola. But for the most part, everything is still well defined, except for the two lines.
Local is a field, yes.
Well, except for the asymptotes, everything is
so
fine.
locally. So you have locally you have the axiom of a field.
Exactly, and that's all you really care about. Well, actually, you handle these nilpotents in a different way, I suppose.
Yeah.
You have a nilpotent, right? What is a nilpotent in ISO theory?
Yeah. I would be, if you don't mind, there are, if I remember well, there are 14 conditions for a field to be verified. I will maybe if I don't bother you, we'll send you an email and ask you which of those conditions are violated by the hyperbolic asymptotically, as you said. Because then is the question whether the axiom can be reconstructed some way. I believe that if that's possible, this formulation, this geometrical representation of special relativity will acquire, much more value, in my view.
Okay, the only other thing you have to watch out for with the hyperbolic numbers, as an observer, of course, you don't have to worry about, you're not going to be traveling at the speed of light. So you
Yes, of course.
basically have the axioms of.
That is correct. Locally, you have everything. Yes, I see it.
That's right.
Yes, locally.
Well, everything except on the asymptotes. That's the speed of light.
Well, I appreciate it because I had ambiguity in my mind regarding this fundamental point, and I appreciate this comments. Yes, indeed.
Well, I'm convinced that there's an extremely close relationship between the ideas. I'd like to discover that or find. Well, we just have to concentrate on.
If I may say so, the same issue occurs between geometry and algebra. One is a different view of the same reality. So there is a connection between geometry and algebra. Of course there is. And so that's the beauty of mathematics, that brings into focus different perspective. Reality is so polyedric. I don't believe there is only one single theory that can represent everything. No. You need different theory that gives you different perspective, and
well, it's extremely interesting. Everything, of course.
It is, yes. It's after a century, more than a century, we're still trying to understand special relativity. It's unbelievable.
Well, yeah, I think part of the problem is the language. And then you have, well, of course, with spoken language. Well, at least there are translators now for spoken language, but it's still difficult for mathematicians to, well, that's why they say mathematics is very conservative. Why is Gibbs Heaviside emphasized so much still, anyway.
Well, that is true. This is the problem that I had when I was at Harvard, MIT. They were fantastic mathematicians and they were fantastic physicists, but very, very few faculty member that could overpass, both. So make the connection. That was difficult to. It's part of the problem the difficulty that I had in communicating with colleagues. Try to locate because my needs were physical from a physical viewpoint, and but that's okay.
Well, I understand very well because I worked with David Hestenes, who's a theoretical physicist. But I did get my PhD in mathematics, but mathematicians would say, well, we're not so sure about this guy. He got his degree working with a young theoretical physicist. And the physicists think, well, we're not so sure. He got his PhD in mathematics, but, so I went to Poland for postdoctoral work. I went to Mexico and, found opportunities. The United States, what they're doing here with education is terrible. First of all, there's all kinds of political problems now that are trying to get free college education for 2 years. They're not going to give anything. It's all neoliberalism.
So, but Hestenes was indeed a magnificent physicist as well as mathematician. He was encompassing both, in my view. He's a good name in science.
Who is that?
My pronunciation, I'm sorry, Hestenes.
Oh, Hestenes, yes.
Hestenes, I'm sorry, Hestenes. I pronounced it the Italian way, I'm sorry.
Okay, well, I think we should say this is the end of the talk for now. I really appreciate very much Garret's presentation today and all of the comments. And
but let me make one more quick comment about this question I put on the paper. What is the geometry behind category theory? For me, category theory is still pretty abstract. I don't understand it. Is there a geometry other than chasing diagrams?
Maybe the graphics. Okay, I think we can speak in another time now.
Okay.
It's a very deep question, I think,
yes.
And that the answer is usually asked in the other direction, like what can you say about geometry using category theory? But there is a lot that you can say in both directions, I think. And okay. I think as Jesus mentioned one of the fundamental notions in category theory is the idea of an arrow, and if as an abstraction, and if arrow is not somehow related to vector, that would be surprising.
Huh. Okay. Well, so that's a question I put at the beginning. I'll send you these things. I'll send you the book and so on, whatever. So
Okay.
how many people are participating right now? I don't see.
There are 6.
Okay, so some people did come then. Later.
Yes, there were two more
Well, I'm willing
participants
to,
after
anyone
we
that's
started.
interested, I'll send a copy of the book. For people that listen to the talk, that's recorded. I understand it is recorded. So I'm willing to
Yes.
give a copy of the book. It's very basic ideas that are discussed.
When I distribute the recording, I'll mention that in the text above, just saying that
it is for personal use only. I don't want it to be widely
yeah,
distributed.
of course.
Yes.
Anyone that's interested, I'll gladly, for their own personal use, I'll send them a copy of the electronic version, of course.
Okay.
Okay, thank you.
Thank you very much.
Well,
Thank you. Very nice lecture indeed. Very, very.
Thank you very much. Thank you. It was amazing, everything. Thank you.
Well, thank you very
I
much.
see Dahlia is here also. We haven't seen you
Thank
for a
you.
long time, Dahlia.
Yes, I'm sorry. I have a lot of things, but I'm here. Thank you.
Okay, good. I'm very happy that you could come.
Thank you. And I want to the book, please. A copy, the lecture, please.
Okay, I'll certainly send it to you.
Thank you. Thank you so much. Good day.
Okay.
Bye for now.
Okay, bye.